Okay, today we're going to talk about the nature of matter. This is chapter 2.1 in your book, which I'd also like you to read. The nature of matter deals with molecular compounds, atoms. We're looking at the building blocks of matter here. This slide is showing just a handful of different ways that oxygen can combine with other elements, and depending on how many times oxygen is present, how many oxygen atoms are present, and what other elements are present, you can get very different properties. For example, if one carbon atom and one oxygen atom combine to form carbon monoxide, we get a very poisonous gas. If two oxygen molecules combine with one carbon atom, well, this is a harmless gas, at least for humans, and a waste material that you're constantly breathing out. So a big difference one oxygen atom makes. And if one oxygen atom combines with two hydrogen atoms, we get the essential molecule water. And add another oxygen to that, and we get hydrogen peroxide, which some of you have used to treat cuts or bleach hair. So depending on the combination of different elements and their number present, we get very different properties. Here's a couple of vocab words we really want to learn. So as we go through this together, I'd like you to write these words down and make sure they're defined somewhere. And those words are matter, atom, compounds, molecules, elements, and allotropes. Know those inside out, and we'd like to compare and contrast them and know the differences between them. So let's start with matter. Matter is, in a loose definition, the stuff that makes up the universe. So what is that stuff? A more technical definition would be anything that has mass and takes up space. And another word for taking up space is volume. So that begs the question, I think, of what is not matter. Maybe you guys can think of some things that would fall under the category of not matter. I'd like you to write those down, maybe think of one or two and bring them in. Again, things that don't have mass and don't take up space, but might still be measured by a scientist in an experiment, things that are quantifiable. Okay, let's turn to the word atom. The atom is the smallest particle that still characterizes a chemical element. And what that means is that, let's say I have a bar of gold. So this is my bar of gold up here. If I slice that gold in half, and slice those halves in halves, and then slice that quarter in another half, and so on, there comes a point where I can't cut it in half anymore. And that point is called it would be called an atom of gold. Atom of the element gold. If you were to cut that in half, and this is supposed to be a more accurate, slightly more accurate picture of an atom, then we would have neutrons and protons. So the smallest division, without literally splitting open up the atom into its subcomponents, is called an atom. And literally it means indivisible, although we now know that we can divide atoms, but we just changed that matter in quite a drastic way. In terms of size, atoms range in diameter from 1 times 10 to the negative 10th, and we call negative 10th an angstrom, to 5 times 10 to the negative 10th. I'm going to circle that and write out angstroms, because we did not learn that last chapter, but you'll commonly come across it. You'll also see it written abbreviated A. And what it means is anything to the power of 10. Remember, power of 9 we called a nanoparticle, and then this would be called an angstrom, and I'm sorry, that's a 10 there. So just to quickly get a sense of how many atoms you might be seeing before you right now, if you were to make a dot on the paper, how many atoms of carbon because carbon is what pencil lead is really made out of, how many atoms of carbon or graphite are lined up along the diameter of that dot, do you think? In other words, I'm going to make an exaggerated big dot. That's your pencil dot. That's a blown up picture of this. Well, if we wanted to know how many atoms are lined up across, we could count that number. We can measure the dot. We know the average distance and diameter of an atom, and we would get 10 million atoms are in that. So quite a large number of atoms in a small space. Atoms are very, very tiny. So let's go on now to the word element. Elements are particular types of atoms. And if we say we have a sample of an element, what we mean is that substance contains only one type of atom. And that atom is defined, what an element is defined by, is its atomic number. Its atomic number is the number of protons in the nucleus of the atom, in the center part of the atom. As you know already, we use symbols to indicate different elements. I'm thinking you know this symbol. This is for gold. So symbols start with a capital letter. They have sometimes 2 letters, sometimes 1. Sulfur, iron. So we use these, and if we said we had a sample of the element iron, then it would mean all of the atoms in that sample of iron have the same number of protons in their nucleus. And protons are a small particle that make up the nucleus of an atom. If we were to line up the elements top 10 wise, top 10 elements in the universe, by far the most common element is hydrogen. So hydrogen goes in this spot. And I would like you to know that. So if we look at the percent of atoms in the universe, hydrogen is the winner, hands down. Let's talk about molecules now. Molecules have at least 2 atoms that are held together by a chemical bond, and those bonds hold the molecule together. Those atoms then act as a unit that we call a molecule. So if we look, for example, at a sample of neon atoms, they don't bond to other atoms of neon, so we would not call them molecules. The pictures, on the other hand, below show water in this example, and then this is a collection of water molecules made up of oxygen and 2 hydrogens. And then this is a larger organic molecule called caffeine, where we see hydrogen, oxygen, carbon, all bonded together in a more complex way. Also a molecule, so they're functioning as a unit. Alright, now this one gets a little more complicated. A compound is when you have 2 or more different, and I'm going to circle that word different, chemically combined chemical elements. And they're in a fixed ratio that determines the composition of our compound. So we're looking here for 2 or more different elements. We're going to look for 2 different symbols then, and the ratio of those elements cannot change. So for example, I'm going to write H2O here. This is definitely a compound. I have 2 different types of elements present, and for it to be water, those elements always have to be present in the 2-to-1 ratio. If you do change that ratio, let's say now we have another compound, and you might know that compound is hydrogen peroxide. Now I've changed the ratio. I no longer have the compound water. We said it was hydrogen peroxide. So the fixed ratio is important in a compound, and then it doesn't change, and if it does, you have a new compound. So as we look at this list, try to copy down that list and give yourself a moment to pick out which of the following are compounds. And what you should do is try to just throw a circle around the true compound. Now these should all be subscripts, but it doesn't come out, so in other words, this should be written H2, sub 2, O. This should be written O3, CH4, this guy is H2, and Fe. So as we look at these, H2O qualifies, doesn't it? Methane, which is CH4, qualifies. Hydrogen does not qualify. plain old iron does not qualify. And this is called ozone. And although you have multiple multiple oxygen atoms present, they must be different from one another. So that one doesn't qualify either. Okay, let's come away from the concept of a compound and look at elements that are pure, elements that don't have any other element present, just one type. Well, it turns out that those elements can get together in different combinations in different ways, and when they do, we call them allotropes. Allotropes are pure forms, so that means you're only going to see one element type present, but they differ quite wildly in structure, ratio, and properties. An example of an allotrope here is O3, so this is oxygen gas that you're seeing here. And then it's also an example, that's ozone gas that you see there. And then this is an example of oxygen gas. And they're very different gases. They have very different properties. So just adding that extra O means that you're changing a lot about the molecule. Then we would call these two things allotropes. So oxygen and ozone are allotropes of oxygen. Carbon is a classic example of something that forms allotropes. Here we've got a sample of carbon getting together in these ring structures. Rings of 6 carbons held together to another ring of 6 carbons, and we call this graphite. And this is what you might be writing with right now if you're writing with a pencil. It's very slippery. These bonds here in dotted lines can shift pretty easily. So we slide sheets of carbon graphite off one another. When you apply some pressure, these bonds here break, and this whole thing might slide off onto your paper. Kind of cool. Another way carbon can get together is one central carbon atom can bond in 1, 2, 3, 4 to branch out in a structure with other carbon atoms, and when it does, we call that structure a diamond. So very strong bonds, network of bonds, very different than graphite, but still made up only of carbon. Okay, our last allotrope of carbon is called Buckminster fullerene, or a buckyball for short. It's a long word. And this carbon allotrope is made up of 60 carbon atoms joined in, commonly people describe it as a soccer ball-like structure of these rings of 6 carbon atoms. It's hollow in the center, and although it has this intricate pattern, it still is only carbon. We said it was man-made, so it's the man-made allotrope of carbon. Only carbon atoms present, so technically it is an allotrope of carbon. Think it for a second why we could never have an allotrope as a compound. Why that could never be. Remember, a compound must, by definition, be 2 different elements. So, back to our example, we're going to choose methane. You have carbon present, you have hydrogen present, so this would be a compound. An allotrope, by definition, can only contain one element type. So we say like carbon can get together to form graphite, it can get together to form diamond, it can get together to form Buckminster fullerene, but it's just that carbon present. So even if it was C60, like Buckminster fullerene, you have 60 atoms present, there is no other atoms present like hydrogen or oxygen. So we would say allotropes are pure elements that can never be called compounds. So let's expand on that idea of a pure substance and what a pure substance actually is and what different classes we could have. Elements, molecules, and compounds are pure substances as long as they're not mixed with anything else. So for an example, we could have atoms of an element. That would be like this first box here. And there's certain types of elements, like noble gases, that just exist as singular atoms moving around in space. So we might pick an example as neon, the gas that you see in signs that light up signs. We also have examples of molecules of an element. Remember, molecules are just multiple atoms that come together. They don't have to be different for them to be molecules. So we might have a molecule like oxygen gas, O2 we would write, that we're breathing in right now. So those would be molecules of an element. And still pure because there's nothing else in the sample. We could also have molecules of a compound. So molecules of a compound, and that might be something like ammonia, methane, water. So let's choose NH3 here. This is a compound. You have both nitrogen and hydrogen present, but if you just look at one singular one, this would be a molecule, a free atom. And if we mixed these all together, if we took a sample of this and we mixed it with this and we mixed it with this, now we have what's called a mixture. Not pure. So not a pure substance, a mixture. A great example of a mixture is air. So what we're breathing in right now. Its major component, about 80% of it, is nitrogen, and about 29% is oxygen. And the rest, that small 1%, is split up. With carbon dioxide, we know that's growing, which is unfortunate. We have argon, water vapor, neon, trace amounts of helium. But the major components are oxygen and nitrogen. But since we see all of these together that are mixed together to form air, we would say that air is not a pure substance.